In this video, I'm going to continue in operation amplifier basics. So how to do a problem. Now, in the previous lecture I explained the ideal op-amp characteristics. Now, what was the ideal characteristics was gain is equal to infinity. Suppose there is a V1 V2 input, so we got V0 is equal to A into V1 minus V2. So if we gain is equal to infinity, so it is infinity into V1 minus V2, so V1 minus V2 will become 1 V0 by infinity, so V1 minus V2 is equal to 0 or V1 is equal to V2. So this is a virtual short or virtual ground concept. Now, since in a different way we can say, to make the gain is equal to infinity, we have to give V1 is equal to V2, right? Or we can say, because gain is infinity, so the two input voltages should become equal, right? So either way we can tell. Now, what type of problems in using operational amplifier the question comes? So I have divided like this. So operational amplifier DC performance and AC performance. And what is the DC performance is, it is like, so how it will act in a DC supplies, or we can say DC performance in the sense what are the input offsets. So input offset voltage, output offset voltage, input offset current, input bias current. Similarly, AC performance is finding gain or bandwidth and slew rate, etc. So these are these two performance. So in these two performance they will give questions like what is the output offset voltage when some input offset voltage is there, etc. Right? Find slew rate, or if slew rate is given, find the voltage change at the output. Now next is oscillators. So using op-amp also we can have RC phase shift oscillator, Wien bridge oscillator. Then they will give find the oscillation frequency or find some R or C values, right? That also we'll discuss. Now one more is filters, active filters. Generally it is called active filters, right? Using op-amp and some external resistors and capacitors, we can build high pass filter, low pass filter, band pass filter, band stop filter, right? Similarly, there is one more domain. It's a comparator using op-amp. So it's open loop comparator. Open loop operation amplifier can act as a simple comparator. That is, suppose V1 is here, V2 is here. There is a plus VCC, minus VCC, V0. Whenever V1 is greater than V2, we will get minus VSAT, and whenever V2 is greater than V1, we will get plus VSAT. So depending on these concepts, they will find some hysteresis width or lower threshold voltage, upper threshold voltage, or using a stable multivibrator and monostable multivibrator, right? For all these type of problems, what we need is, so I need a KCL, nodal analysis and mesh analysis. These concepts I need. If we don't know these concepts, how to apply, then we cannot do the problems in this using operation amplifier, right? So once we drawn a small signal model in op-amp, then I need only these four. I cannot say all at a time, but maximum I will use the nodal analysis. Sometimes I will use mesh analysis, right? So anyway, KCL, KVL is part of the nodal only. So I need these four concepts: KCL, KVL, nodal analysis and mesh analysis, right? Now, so once we know this, so what I start with is filters, active filters. See, in the gate we can see in every time, so they will ask identify the filter type. Generally the questions will come either high pass filter or low pass filter. So questions comes like this. So this was gate 2011 and this was some gate problem 2004 or something. This is also gate problem, and this one is like example. Now before start with these questions, so we need how the capacitor and inductor will behave in S domain, or we can say what is the equivalent impedance in S domain. So C can be replaced by 1 by Cs and inductor is replaced by S into L. Once we know this, it's easy to identify which filter type. Now there is a blind rule, or we can say steps. Now step 1, replace this capacitor with impedance, that is 1 by SC, right? That is a step 1. Now that is step 1 is capacitor is replaced by 1 by CS. Second step is substitute S is equal to 0, that is low frequency. J is equal to j omega, so omega equal to 0. Now step 3 is put S is equal to infinity, that is high frequency. So when you substitute this and see the behavior of this circuit. Now when S is equal to 0, 1 by 0 is, it will become infinity. That means this is a simple behavior like a open circuit, and this is a resistor. This is equivalent model. Now when there is no path between input and output, that means I will get in a step 1 V0 is equal to 0. That means no output is we are getting. Now when S is equal to infinity, high frequency, so the equivalent model will become as a short circuit, right? 1 by infinity 0, so impedance is 0 means it become short circuit. Then there is a resistor, then VA. Now VA is passing through this resistance path to V0. That means I am getting V0 some finite value. Now if you draw this from omega and this gain, so initially there is no voltage or gain, but in the high frequencies I am getting some gain like this. So what is this filter? Simply high pass filter. So this is the how to find the filters using operation amplifier. Now if you see this one, I can go very fast. How to identify is simple. It is replaced by S into L1. Now if you see, if you put S is equal to 0, it will become simply short circuit. So short circuit means I need to apply a virtual ground concept. So plus terminal is 0 volt. That means minus terminal also will become 0 volt. Whenever there is a short circuit, so this resistor will be replaced by short circuit. That means I will get V0 is equal to 0. So this is a short circuit. So when S is equal to 0, it will become a short circuit. Now when S is equal to infinity, that is impedance is infinity, that means it will become simply open circuit. So whenever there is an open circuit, now it is a path like this, right? So that means V0 we are getting some value. So V0 is equal to some finite value. Again it is a low pass filter only. No, V0 is, so it's not low pass filter, it is high pass filter only. So when S is equal to 0, I am getting 0, so there is no output. When S is equal to infinity, I am getting V0, so finite, so it is a high pass filter. Now the last question I can go here is this one. Now again same procedure, you can apply for any question this rule. So this question was when it was come, yeah, so it's a gate 2007, it's a gate 2007 problem. Now again replace this capacitor is S1 by SC. When S is equal to 0, so it will become open circuit. So when this is open circuit, but there is a resistor through this VA, that means I will get V0 a finite value when S is equal to 0. When S is equal to infinity, it will become short circuit, right? Still this is a 0 volt, but 0 minus Vi by R, 0 minus V0 by R, still I will get a finite value. That means for all frequencies I am getting the finite value only. That means so it is a all pass filter, right? So what is the condition? When S is equal to 0, it will become short circuit. So 0 0, so I am getting a finite value. When S is equal to infinity, so it's open circuit, still I am getting the output as finite value. So that's why it is all pass filter. So you may get doubt, so it may be band stop filter also. That is, band stop filter will become like this, the frequency response. But if you observe this circuit, for all frequencies there is no stopping at all, right? So that's why it is a all pass filter only. But band stop filter will behave in a small, at a particular frequency there is a 0 gain. But by looking this, we can say there is no 0 gain when in intermediate frequencies, right? So that is why it is a all pass filter. Now in the next video we will see how how to find the transfer function for all the filters. This is like a blind rule to identify, but if they ask find the cutoff frequencies, so I need a frequency response, right? So that we'll see in the next lecture.